Okay, we're going to start a new topic called buckling. You've all experienced it in one way or another. If I have a long, skinny member and load it axially, then what will happen to it, or what may happen to it, is that it bends like this. And that sort of explains to a certain extent, it's similar to a bending problem. In other words, if I were to rotate this 90 degrees, what would we see? Oops. Okay, one more time. See if I can get this right here. I want to rotate this thing. I guess I can't do it, but if you look at this, if you look at this sideways, you can see it looks like a beam that's bent. So this particular shape that it takes is a sine wave. And what we're going to do is we're going to derive the buckling equation, and I'm going to start by setting up a coordinate system. Now, this is my x direction. I'm taking that as my x direction, which again is similar when we're doing a beam. We take the x direction along the length of the beam. I'm going to call this direction perpendicular to it v, small v. We're going to apply a load P. It has a length L. And what I'm going to do, so now this is bent. I've applied the load, it has bent. And I'm going to make a cut through here. And so, in other words, I'm going to take this portion and I'm going to represent it here. And maybe make this a little more clear. Oops. So this is, what do I do? Well, as I always do, when I made a cut through a beam, we always had what? We always had V, N, and M. So we put those same on here. And I'm going to call that point A. Now the distance point A is we're going to call that distance v, small v, as I said. And so if I take moments about point A, we don't need that, we don't need that. We end up with this expression here. So taking moments about A, the sum of the moments about A equals 0. We have what? We have P times V. So I'm taking moments about this point. I have P times V. Plus M equals 0. I rearrange that and I get M is equal to negative P times V, and I'm going to call that equation 1. And as a little bit of an aside here, something that I haven't talked about too much, but if we look at I'm going to define a term. I'm going to call it bending stiffness. EI is bending stiffness, the product of E and I, where E is Young's modulus and I is moment of inertia. It's called bending stiffness. Why do we call it bending stiffness? Because if we want to reduce deflections in a beam, for instance, we want a big I. Another way to reduce deflections is to increase E, make the material stiffer. So the product EI we refer to as bending stiffness, and it comes out in these equations that we develop. I'm not going to go through, or we talked about it in class, that when we look at a beam, that if we look at our moment diagram and integrate it 2 more times, we end up with the deflected shape of the beam, an equation for it. The elastic curve, sometimes it's called. So in other words, I have a beam that has a deflected shape that looks like that. I can write an equation for that. Y is equal to f of x for that shape. You know, it sort of looks like it might be a parabola or something like that. So that means that what? If I follow this, that means that the second derivative of y with respect to x is equal to 1 over EI times m. What does that mean? And in other words, if this is true, then, you know, integrating it once, I get dy dx is 1 over EI times the integral of m dx. I integrate it again, and I get that y is equal to the integral of m dx times 1 over EI. 1 over EI is the bending stiffness, and that is the factor that we need to put in here to account for the properties of the beam itself. So we're going to work with, so this is the equation that we've been talking about all semester, and in a sense, if we differentiate it twice, we get that. So I'm not going to rederive that or anything, so I'm going to leave it as that. Okay, so we're going to use this equation, and we're going to use this also to develop the buckling expression. So for buckling, we have, instead of y, we're using small v. So I'm going to use that equation in this form. So rearranging this, I get m is equal to EI times the second derivative of v with respect to x. I'm going to call that equation 2. And I'm going to substitute equation 1 into equation 2. And I get that, I get negative p times v is equal to EI times second derivative of v with respect to x. Rearranging this some more, I get this. And then dividing by EI, I get that. And you may recognize this differential equation from your differential equations class. You studied it in the form that looks like this: the second derivative of v with respect to x plus this lambda squared times v equals 0. So it's the same thing. So in other words, this is the equation from your differential equations class that you've already solved. And this is our equation, so I'm comparing those two. What do I see? I see that lambda squared in your differential equations class is the same as p over EI for our differential equation. Like I say, you solve this differential equation, and we can get the form of the solution. So we want, in other words, we want v as a function of x to solve this equation. And if you recall, when you solved this in your differential equations class, lambda was a constant, and it's a constant for us. It's p over EI. The solution, we will use the sine-cosine form of the solution of that differential equation. And that form is v is equal to c1 sine lambda x plus c2 cosine lambda x. And we will get c1 and c2 using boundary conditions that we'll get to. And as I said, lambda squared is p over EI, and v of x is the shape of the deformed column. It's a sine curve. Okay. All right, so let's look at the boundary conditions. So if we have a buckling situation, shape looks like that. I have my coordinate system x and v. This is the length L. And what do we see? Looking at that shape, at x equals 0, v equals 0. And what we're going to do is we're going to plug that into our solution form that we just came up with. So we have v equals 0, that goes there. Now we have x equals 0 here. Well, C1 sine of 0, what's the sine of 0? Sine of 0 is 0, so this particular term disappears. Now we have the C2 times the cosine of 0. Well, the cosine of 0 is 1. So I can solve for C2, and I get C2 is equal to 0. So then we put in the other boundary condition, which is up in here, which is that when x equals L, v is 0. So look at that boundary condition at x equals L, v equals 0. I plug that in. Well, I know C2 is 0, so I eliminate the second half of my equation. And so I end up with 0 is equal to C1 times lambda L. And C1 can't be 0 because that would be the trivial problem. So I get that the sine of lambda L equals 0. What does that mean? That means that lambda L has to be, some integer multiple of pi. So if lambda L, for sine lambda L to be 0, lambda L can be 0, pi, 2 pi, 3 pi, ... n pi. And that would be trivial, so we don't consider 0. So basically, lambda L is equal to n times pi, where n is an integer greater than 0. So rearranging that, I get lambda is equal to n pi over L, which means that lambda squared is n squared pi squared over L squared. And then we previously said that lambda squared was p over ei. So I get that p over ei is equal to n squared pi squared over L squared. I rearrange this and I solve for p essentially. I get p is equal to n squared pi squared over L squared times ei, where n is 1, 2, 3, ... And p is the load that initiates our sine curve. So p is the load that initiates buckling. Our interest is in the lowest value of p that's going to cause buckling. So we're interested in the n equals 1 situation. So even though we have all these other numbers out here, we really don't care that much about them. Well, we'll see. We'll add a little bit to this. But in any event, we can define what we're calling p critical. In other words, the lowest value of p is pi squared ei over L squared, using the n equals 1. What do the n's mean? Now, just to let you know. So n equals 1, we get bending, or I get, the buckling shape that looks like that. N equals 2 is going to give us this. And here I've shown some constraints to make it do that. N equals 3 gives us a shape that looks like that. Again, we need constraints to make it do that. It's not going to do it naturally. And we're going to introduce the concept when we put in these constraints of the effective length, so that we have, when I put in those constraints, that would be the effective length there. Now, we are in search of the lowest p In other words, the n equals 1 situation. But when we design our column, we want to design it in such a way that we create a big P critical. A high P critical is what we want, because we want a large number to represent the load at which buckling begins. And the easiest way to think about it is that P critical is a property of the column. In other words, you should think of P critical in the same way that you think of any other material, well, a beam property or column property like the moment of inertia or the Young's modulus. Think of P critical as the property of that column. People get confused with the meaning of P critical after we go farther in this, and you don't want to get confused about the meaning of P critical. Okay, boundary conditions can be different from a pin. And what do I mean by that? In other words, what we've shown here is, we've begun our analysis with a pin-pin condition. In other words, I have my column, it's pinned at this end, it's pinned at that end, and when it bends like that. That's your base case. And we're going to call that K equals 1. As another boundary condition, we could have a pin fixed condition. And what does that mean? That means that we have a pin here, so the column is free to rotate, but if it's fixed here, it goes straight out. That's a pin fixed. And if we look at it, what we find is that we get this sine curve, but the sine curve is over a distance of 0.7 L. And so we have a K equals 0.7. In our original one, we had this whole thing was a sine curve. That's why we had K equals 1. So when K is equal to 0.7, we can think of it having an effective length of 0.7 L. If we have a fixed boundary, then what? Then it goes straight out there, it goes straight out there, and then the curve begins. And so we end up with the sine curve over a distance 0.5 L. So we get a K equal to 0.5. If we have a fixed free condition, and this is our flagpole problem, in other words, we have a flagpole sitting here and we load it vertically, well, what happens to that flagpole if we overload it? Well, what it does is it just drifts like that. And so we would see the sine curve over this huge distance, and that would be 2L. So that gives us a K equals 2. I want you to memorize these K values. They're pretty straightforward. You have the easy ones. You have the K equals 1, that's our base case. The K equals 2, that's an easy one. And the K equals 0.5, that's the fixed. The only hard one to memorize is that one, is the pin fixed, which is a K of 0.7. So we're going to call KL the effective length, and that means our expression is that P critical is pi squared EI over the quantity KL squared. And that's what I also want you to memorize, is this P critical. Pi squared EI over KL quantity squared. All right, so how do we work this? How do we work a problem that we're given? Suppose I have a column. It's loaded 200 kips. It has, it's pinned at the base. It's free to rotate at the top. And therefore we get this half a sine curve, or get the sine curve there over that entire length, and the length is 120 inches. The given information, this is all the given information here. Well, let's see, actually. This is the given information right there. And I'm giving you the cross-section of the column, 10 inches by 4 inches. And that the Young's modulus is 5 million psi. And the question is, does this column buckle under the given load? Okay, so let's do the solution. We're going to use our basic equation that P critical is pi squared EI divided by KL quantity squared. And one of the first mistake that people often make, and one you want to avoid, is notice that, as we know, there is more than one moment of inertia for our cross-section. For instance, I could take the moment of inertia about this axis, I could take the moment of inertia about that axis, and in reality we could take it about a bunch of different axes. But what we're interested in is the smallest I. So in other words, if I give you something like this, you happen to look at it, and I want you need to take both of those moments of inertia. So in other words, you have to look at it this way, and you have to look at it that way, based on the way that we've been doing moment of inertia. So I have two moments of inertia here. 112, they're both 112 BH cubed, but if I'm looking at this one, 112 BH cubed is 112 4 times 10 cubed. If I'm looking at this one, I'll see 112 10 times 4 cubed. Well, which is the smallest of those? Well, the smallest one is for this case. So I think that's obvious because we only have 4 cubed. Here we have 10 cubed. Here we have 4 cubed. The 4 cubed is going to be much smaller than the 10 cubed. So when I use my equation to get I, I'm going to have 112 10 times 4 cubed. And notice my K, the K for this is 1 because of this shape here. And so K times L is simply going to be 120 inches. And I now plug it into my expression. Pi squared is obvious. E, I've given you that. I, 112 10 times 4 cubed. KL, 1 times 120 squared. And I get a P critical of 183 kips. Now, what does that mean? That means that if we apply 183 kips, that column buckles. So like I say, you want to look at, one of the best ways to look at this is to think that P critical, that's a property of the column. The same thing that E is a property of the column, and I is a property of the column. This P critical is a property of the column. So you say, okay, I'm using a column that's got a P critical of 183. Now I'm going to look at my load. What do I see? Well, I'm applying 200. So what does that mean? I'm applying more than what P critical is, and therefore this one buckles. So the answer is yes, that buckles. Now, I want to remind you of how to do these moments of inertia because it's been a while since we've done them. But again, I just went through the rectangle is pretty easy. You know, if I give you a rectangle, what does that mean? Well, you have to take the moment of inertia, the smallest moment of inertia, and that's going to be the the way that makes it look with the largest base. Now, what happens if we use an I shape, or wide flange shape, or an I-beam? Then I have to compute the moment of inertia this way, and I have to compute the moment of inertia this way. If you remember how we did the I before, we created a box, and it's 112b outer h outer cubed minus 112b inner h inner cubed to get the moment of inertia for this shape. And just as a reminder, if I take and I turn it sideways, then what? Then I have my two flanges here. So that's going to be, and well, notice, all of the, with this situation, the centroid of the left piece, the centroid of the right piece, and the centroid of the middle piece, they all lie on the centroid of the overall beam cross-section. And that means that the D's, D1, D2, D3, they're all 0, because all the centroids line up. So this is a very easy moment of inertia to compute. It's 112bh cubed for the two flanges, plus 112bh cubed for the web. And so most of the time this is going to give us the smallest moment of inertia, but under some circumstances it may not. So if I give you a column that is like an I-beam, then you need to compute both moments of inertia, and you choose the smallest of the two for buckling. And this is the details of, you can pause the video, look at the numbers here. Okay, so what I want you to do is this problem. Again, find P critical, does this buckle? Here's your information. There's your cross-section. This is the situation. So what I want you to do is to pause the video and solve this problem. Okay, I've assumed you've solved this problem. Let's do it. So we know our basic expression is P critical is pi squared EI over KL quantity squared. And what do let's look at the KL portion. Well, what is it? It's fixed. Well, this would take a shape that looks like that, which means it's fixed here. It's free to rotate here, which we call pin. And so this is a fixed pin, which gives us a K of 0.7. So it's 0.7 times 20 quantity squared in the denominator. Then we have pi squared, E is given. And then what is my I? Well, to do the I, what do I have to do? I have to take I don't want to use it like that. I want to do, this is, 0.5. I want to do it this way, 0.1. So I get 112, B is 0.5 from there, times 0.1 H there, cubed. So we end up with, when we apply all of this, we get P critical is 62.9 kips, which means, like I say, that's the property of the column in a sense. And since we are only applying 40 kips, not the 62.9, that then, does not buckle.